Okay, I think we can start. And today I'm gonna talk about homework 2, the first two questions about homework 2. And okay, so for problem 3.16, you have to compute the minimum number of semesters to complete the curriculum. So first you have to detect whether there's a cycle or not. If there's a cycle, you can't complete the curriculum. But this step is not mandatory because you can just assume that there's no cycle. Yeah, and then if there's no cycle, you have directly a cyclic graph. It looks like this. So what we need to do is to find the longest path here, and that's the number of semesters you need to complete the curriculum. Because, for example, for this node, it has two paths. One is this one, and one is this one. But this course should be taken in third semester, because this course should be taken in the first semester. This one in the second, and this one has to wait until third. So you need to consider the longest path in order to fulfill the requirement. Okay, and so and here is a possible way to compute the longest path. There's many other ways, and any of that is okay as long as they runs in linear time. Here, degree is the number of prerequisite of course I, and DI, we use DI to recall the earliest time that a course can be taken. And we use a queue to store all the courses with degree 0, which means we can take them immediately. And every time you will get an X from Q, which means you can take it, and then you update all the courses that has X as its prerequisite. For example, 1, 2, 3. If you after getting node 1, you can update node 2 and node 3, and then you need to update the distance, the degrees of node 2 and 3, and check whether you can put them, whether they are available now. For example, here 2 will be available and you need to put it into the queue, but 3 is not. And after this process, the answer is max DI. Do you have any questions? Yeah, so I'm not sure about if you want to delete source node, you need to do it like in a, okay, say, yeah. For example, if you have this, this is the graph. You have to do it at the same time. For example, you have two nodes that doesn't have two nodes that don't have any prerequisite. You delete them, and then you have 3 nodes, and this will be taken in the second semester, and then finally you have 2 nodes and that don't have any prerequisites, and then you have 2, 3. And what you need to do is to make sure the running time is linear. This is the most important part. As I said, there's many ways to do it. Yeah, you have. So, for example, you can't check every node each iteration. first you have this. So for example, you write a while there's still causes, then you will for all the nodes you check whether it has any prerequisite or not. And if you do this, then it's definitely not linear time. Yeah. Mm-hmm. Okay. And if you don't have any more questions, we can go to next problem. For this problem, A is incorrect, and this is an counterexample. So this is a graph with 4 nodes, and it has 4 edges, which is greater than 3, so it meets the requirement. And 2 is the unique heaviest edge, but this edge should appear in every MST, because otherwise the graph will be disconnected. So A is incorrect. Okay, so let's look at B. B is correct. We can prove this by contradiction. So you can, it says if G has a cycle with a unique heaviest edge E, then E cannot be part of any MST. So you can assume that if we have a MST with edge E, let's say edge E connects U and V in the MST. So, and because this is a cycle, this edge has a cycle. First of all, the whole cycle can't appear in the MST at the same time, because otherwise, so MST is a tree, it can't contain any cycle. So you can always find an edge that is missing in the MST. And so this edge has a smaller weight than E. So you can just delete E and add the edge, the missing edge here, and you obtain another spanning tree which has a smaller total weight than this MST. So this means your assumption is incorrect. E is not in, so it's not in the MST, because if you can obtain a smaller MST, it means your original MST is not an MST. So your assumption is there's a contradiction. Okay, and let's look at C. C is also correct. Let E be the any edge of minimum weight, then E must be part of some MST. Some MST here means you don't have to, it doesn't necessarily appear in every MST, but some of them. You can start with any MST without edge E. So let's say this is edge E, but it doesn't appear in a MST. And so it must be connected by some other edges. We can first find the path from U to V, and then because it has the minimum weight, so you can replace any edge on the path with E. Yeah. So so actually all the edges on the path should have the same minimum weight. And so you just replace, for example, I delete this one and I add E. And it's another MST with E. So you can always construct MST like this. So E must be part of some MST. Okay. And D is also correct, and we again prove by contradiction. If the lightest edge in a graph is unique, then it must be part of every MST. So you can assume that if there's a MST without HE, this is a MST without HE. Again, we will find the path. We will find the path between U and V, and because HE has the minimum weight, and it's unique. So any edge in the path of U and V will be greater than edge E. And if you delete any edge in the path and reconnect E, you can have a smaller MST, which means the original MST is not an MST. So your assumption is incorrect. E must be in the MST. So D is correct. And let's go to E. If E is part of some MST of G, then it must be a lightest edge across some cut of G. This is correct because we know that there's two rules, blue rule and red rule. And if you repeat them again and again, you can finally get a MST with like blue edges from MST. And so if it is an MST, then you can do it. You can obtain it by repeating these two processes. And in order to color it blue, it must be the minimum weight of a cut, of some cut. So if E is part of some MST, then it must be the lightest edge across some cut. And finally, for F, this is incorrect, and here's a counterexample. The middle part is a cycle with unique minimum, unique lightest edge E, having weight 2. But the MST is actually this one, with all edges with weight 1. So this edge doesn't appear in any MST, and F is incorrect. Do you have any questions? Okay, let's go to the next problem, 5.11. So initially you will have 1, 2 to 8. They're not connected to any of the any other node. And the first 4 operations will give you this result. You have to connect 1 and 2, 2 and 3 and 2, 4, 5 and 6, 7 and 8. And so there's actually ties here, and you have to make the lower numbered root point to the higher number root. So you will have 1 pointing to 2, 3 pointing to 4. And this is the result after the first 4 operation. And then after the next 2 operation, you will have this. So first you want to union y 1 and 4. So you first have to find the root for 1, which is 2. And then you find the root for 4, which is 4 here. And you connect them again, there's a tie, so you have to point 2 to 4. And it's the same for the operation union 6, 7. And then we will union 4, 5. So here we have to, we first still have to find the root for 4 and 5. And so, and here so if you do path compression, you might have this one. So from like this part, because you have this operation, you will have this one. Or I think according to the textbook, it doesn't do path compression for this node. So it's okay if you don't have this, just following the textbook. And again, there's a tie, so you have to point 4 to 8. And then you the last operation is to find 1. The result is 8. So here, when you are finding 1 and you do path compression, so 2 will be pointing to 8, and 1 will also be pointing to 8. But if you, like as I said, if you follow the textbook and if you have this, it's also correct. Okay. Do you have any questions? So we follow textbook, it might look like this. Okay, if you don't have any questions, we can go to next problem. So we want to find the Huffman encoding here. Basically, we need to merge nodes with lowest frequencies. And so first of all, we'll merge D and E, and then we will merge it with C. And again, we'll merge it with B, because every time we will just choose 2 lowest frequency nodes. And finally, we'll merge it with A. This is 1. And then you can give a, like, you can give this edge 0, this edge 1, or you can give this edge 1, this edge 0. Anyway, it's okay. And so there's many possible answers. Any of them is correct. And this is one possible answer. I give 0 on the left and 1 on the right. Yeah. But anyone is okay. And for the problem B, you want to know the length of the encoded file. So for A, you have the frequency is 1/2, which means you have 1/2 times 1 million A's. And you have this number of A, and each A contains 1. And then this is the length of A. And also you can calculate for B. 1/4 times 1 million is the number of B, and the length is 2. Okay. So finally the formula is here, and the result is here. Do you have any questions? If you don't have any questions, we can go to the next problem. You have to find a lightest spanning tree, and all nodes in U are leaves. So here's the hint. If you remove nodes from U, then what will from the optimal solution, what is left? It's pretty straightforward. If you I think if you remove leaves, remove this one and this one, there will still be a tree. And so this gives you an idea of how to do this. You can first find an MST for the graph V minus U, which means deleting all nodes in U, deleting all nodes from U in V, and you find an MST. And then after T is the MST you find, and for every node in U, you just need to check and find the minimum edge that connect this node and T, and connect them. And then this one will be the final answer. And for the time complexity, so the first step is finding MST. It's exactly the same as required here. And for the second step, we need to do is to examine all the edges, uh, about nodes in EV. So the running time is OE. So, and the running time is dominated by the first step. And we meet the requirement. And the last, not the last, but for this question, you need to find an order to serve customers. The best order is actually uh, according to their service time. You just need to sort customers according to their service time, and then you serve them in order. This will result in minimum total waiting time, because you can see that if this is the first customer, this is the second one, this is the third one. And for the first one, you have to serve it for time T1. Then all the customers have to wait for T1. Customer 1, 2, 3, and then you serve customer T2. Only customer T2, only customer 2 and 3 have to wait for T2, and only customer 3 have to wait for T3. So if you write it down as a formula, you will have this. For the first customer, there's total n minus I plus 1 customers. They have to wait for this amount of time. And so as you can see here, if a customer is served earlier, the serving time is more people are waiting for this serving time. So you want to make it smaller. So what you need to do is just to sort all the customers and serve them according to their service time in your sending order. Okay, and here's the last question. You have to support addition and deletion of edges and maintain MST. Okay, so first of all, the third operation, weight change of edges. You can use A and B to do it. You can first delete the edge. And then you add a new edge with a new weight. So, and then you can use A and B to finish C. And what you need to do is to work out how to do A and B. For A, if you have this is the edge U and B, and it's the weight is W. You have to first find the path in the MST between node U and V, and you need to check the maximum, the heaviest edge on the path. For example, it's this one, and you need to compare this weight to T, which one is smaller, and we keep the smaller one. If W is smaller than the original edge, then we will delete this one and add W. Otherwise, we will just keep the original one. And in this way, we successfully maintain the MST. And for B, deleting, you first have to check whether this edge appears in the MST. If it doesn't appear in the MST, then deleting it doesn't affect the MST. You just need to delete it in G. And if it is in the MST, then deleting it will result in two connected components. So maybe it looks like this. And what you need to do is to connect these two components with the minimum weight. And you need to find, you can just check all edges and find the one that is across two components and has the minimum weight. And you connect it so you maintain the MST. Yeah, and that's how you deal with AFE. And we are done. So do you have any questions?